Okay, this is more balancing practice with acidic solutions, and I've copied out the reactions already because I think this one's going to take a little while and you might be a little tired of the sound of my voice by the time it's over, so we'll cut the time down as much as we can. So, let's get into our steps here. Step 1, other than oxygen and hydrogen, balance everything you can. Arsenic, 1 and 1, good. Bromine, 1 and 1, good. Next, oxygen, 3 on the left, 4 on the right. You add oxygen by adding water, so we need a water over here. Down here, 3 oxygens. I need 3 oxygen on the right. Just add water. Hydrogen next. There's 2 hydrogen on the left here, so we need 2 on the right. It's an acidic solution, so you're adding H+, not elemental hydrogen. And here we have 6 hydrogen on the left, so we need... 6 on the right, so we need 6 on the left. Next, charge. I have a total of -3 charge on the left of this one. Fit that in up there. And -3 plus 2, -1 charge on the right. So we need to drag down the higher side by putting 2 electrons there. In this reaction, we have -1 plus 6 is 5 electrons on the left side, and we're at -5 total charge on the left side, -1 on the right side. So we must drag this side down with 6 electrons. By the way, the fact that these hydrogens and electrons match, that does happen sometimes, but it doesn't happen consistently, so please don't think that's a rule. It's something that you will see from time to time, but don't think just because you're writing a certain number of hydrogens that the electrons are going to be right next to it in the same number. That's not the case, although it did happen twice here. Now, if we're adding these up, we need our number of electrons to match. Here we have 6, here only 2, so the solution is to triple this entire top reaction. So we're going to have 3 times as much there, 3 times as much, 3 times as much, 3 times as much is 6, and 3 times as much is 6, and now we can add those together. For now, I'm going to spare you just writing out the combined reaction here. I think that part's pretty easy. I will do it at the end, but I'm not going to make you watch it now. Let's get on to our next example. It's probably not the part you're most interested in seeing. Okay. Phosphorus, 1 and 1. Iodine, 2 and 1. Uh-oh. There, that's fixed. Now, oxygen. In this reaction, I have 3 on the left, 4 on the right, so the left side needs 1 more oxygen. And there it is. Second reaction, no oxygen on either side, that's perfect. Hydrogen, 3 on the left, only 2 on the right, so the right side needs 1 more hydrogen. There we go. Hydrogen, none and none, that's good too. So now we get to charge. We have a total of -2 charge on the left side of this first reaction, and here we have -1 plus 1 is 0. So between -2 and 0, 0 is actually the higher amount. This is the side we must drag down. We give that side 2 electrons. Now both sides are -2s and those match. Down here, we have 0 charge on the left, -2 on the right. So again, we give electrons to the higher side to drag it down. There we go. And here we catch a break. The number of electrons matches already. We don't have to multiply either reaction. We've already got the electron compatibility that we need. So that one's done other than recopying. Let's go pink. Okay, so here, iodine, because we're looking at the non-oxygen, non-hydrogen stuff. 1 iodine, 2 iodines. That's no good. Fixed. And sulfur, 1 and 1. That's good. Next we balance oxygen. 6 oxygens on the left side, so we need 6 on the right side. And down here, 2 oxygen versus 4 oxygen. The left side needs some help. It needs 2 more. There we go. Now hydrogen. No hydrogen at all. 12 hydrogen, so we need 12 more on the left. So the amounts of hydrogen are equal. And here, 4 hydrogen versus none. The right side needs some help. Needs 4 hydrogens worth of help. And finally, charge. Minus 2 charge from the iodates. Plus 12 there is a total of 10. And on the right side, 0 and 0 is 0. So this side is 10 too high. We will drag it down with 10 electrons. Second row, we have no charge at all on the left side. And on the right, we have, let's see, minus 2 here, plus 4 here, total of plus 2. So we'll drag that side down by adding 2 electrons to it. And last one. For balancing the non-O, non-H stuff, we have nitrogen 1 to 1. And here we have iodine 1 to 1. So those are both good. Oxygen is next. 3 oxygen on the right, only 1 on the left, so this side needs 2 oxygens. 6 oxygen versus only 3. The right side needs 3 oxygens. 3 more oxygens. Good. Now hydrogen. 4 hydrogen on the left, only 1 on the right, so the right side needs 3 more. And for down here for hydrogen, we have 5 versus, what is this? 6 plus another 1 is 7 on the right side versus only 5 on the left side. So the left side needs 2 more hydrogen. Okay. That takes care of the H's. And finally, charge. NO and H2O, that's no charge at all. On the right side, we have plus 3 charge. So we'll drag this side down with 3 electrons. Second reaction, we have plus 2 charge on the left, 0 plus 2, and on the right, no charge at all. So the left side needs 2 electrons. We need to match up our number of electrons. And unfortunately, the numbers are 2 and 3, so just like with fractions, you have to find a lowest common multiple for this. We have to take both of these to 6 electrons. That's the simplest way to make them both match. And that means we have to double the entire first reaction. So twice as much, twice as much, twice as much, twice as much, and twice as much. And for this reaction, we triple everything. So 3 times as much, 3 times, 3 times, 3 times, and 3 times. Okay, so that's all those half reactions balanced. For the next part, I'm just going to be quiet and write the total reactions in case you want to see that, but probably you find that part pretty easy. You may not need to watch. For F, I forgot to match up the electrons, so better do that. We've got 10 in the top row, only 2 in the bottom row. So before we do anything else, times 5, times 5, times 5, times 5, times 5. Good. Okay, back to our scheduled scribing. Okay, if you stuck with me through all that, you might be wondering about something called spectators. And if you were, yeah, you're right. And I'm going to go back and attend to those now. If you have a chemical reaction where there's a species that's there before and it's still there afterwards, unchanged, we call that a spectator. Think of it like at a sporting event, the spectators are the ones who sit on the sidelines and they watch, but they don't actually participate. That's what they mean with spectator chemicals as well. So if you have something like 3 water here and there's 3 water afterwards, you can actually cancel those out. They did not meaningfully participate in the reaction, so you can get rid of them. So this 3H2O is a spectator. You can get rid of that. Also, in this reaction, we had 6H pluses on both sides. You can cancel those also. So with those things gone, you get a much simpler reaction that would just have the ASO3s, the BRO3s, and these finished products at the end. I'm not going to recopy it. I don't have the space, but just erasing those or recopying it without them will get you there. In this next one, let's see, H2O, nope, I2, H plus, no spectators in the next one. Here, we have water counts as a spectator, and so does hydrogen actually. The numbers of these do not necessarily have to match. If you have 10 water before and 6 after, it is legal to say that 6 of these waters are spectators. And just like in math class, if you had like a 10x on one side and a 6x on the other, you could say, I'm going to cancel these 6 waters. They're gone. And here I'm going to cancel 6 of these waters. So there were 10. Now there are only 4. That also happens here with hydrogen ions. We had 12 on the left, 20 on the right. We can say I'm going to cancel all 12 of these, the lesser number, gone completely. And over here, I'm canceling 12 of these hydrogens. So there were 20, I canceled 12, only 8 remain. And does that happen down here in the last one? Yeah, we get the water again. 4 water here and 9 on the right, so we can cancel 4 of those. Goodbye to those 4 waters. And over here where we had 9, we've canceled 4 of them, only 5 left. And, oh, and we get a nice one down here. This reaction has 6 hydrogen on the left and 6 on the right. We can throw those out completely. And there it is, finally, done.